Okay, these diagrams kind of depict the situation. We've got this strip of tin that's 20 inches wide or long, and we're going to bend up the edges to create a trapezoid, probably with an open top. And we're going to make the assumption that it's going to be an isosceles trapezoid. So we're bending up the same number of inches at each edge to create this base at the bottom with a length of 8. So that means each of these legs of the isosceles trapezoid is 6. And the amount that you bend up at each of these vertices of the base determines the area of that trapezoid. And you can see over here we've got an area of 51. Over here we've got an area of 52. Somewhere there's a theta that determines the maximum area of that trapezoid. That's what we got to figure out. What value of theta will maximize the area of that trapezoid. So the formula for the area of a trapezoid is the height times the average of the bases. Again, we're going to do everything depending on this theta. This angle up here is theta also because they're alternate interior angles for transversal crossing two parallel lines. So the altitude, the distance between the bases, is 6 sine of theta because the sine of theta is h over the hypotenuse. This little portion of base 2 is 6 cosine of theta, but there's 2 of them. And of course, if we picture these perpendiculars, then this middle section of base 2 is 8. So down here, we're substituting into the formula. A is the altitude, 6 sine of theta. Here's base 1. This is base 2. 8 plus 2 of these 6 cosine of thetas gives us 12. And if we add the 8 and the 8, 16 divided by 2 gives us this 8. 12 divided by 2 gives us this 6. So there's a formula for the area of that trapezoid depending on theta. And we want to find out the value of theta that maximizes the area. So here's the A formula again. Here's a picture of the same trapezoid, but this time the picture has us at the maximum, 57.33 is the maximum area of that trapezoid when theta is 1.11 radians or 63.4 degrees. Okay, so how do we do that? Well, the derivative we can find using the product rule. So it's the first function times the derivative of the second. Of course, the derivative of the 8 is 0. Plus the second function, 8 plus 6 cosine of theta times the derivative of the first, 6 cosine theta. If we distribute this 6 cosine theta and multiply these factors together, there's a formula for the derivative. Okay, we want to know when does that derivative equal 0 so we can find the critical numbers. Where's the tangent line got a slope, a horizontal? Where's the tangent line horizontal? You might notice that every one of these factors or terms is divisible by 12. So that's what I did down here. 3 cosine squared minus 3 sine squared plus 4 cosine theta equals 0. I see that if I could get everything in terms of cosine, then I might have a quadratic equation. So for sine squared, substitute 1 minus cosine squared, distribute the negative 3, combine some similar terms, and there's the equation we want to solve right there. Doesn't factor, so consider using the quadratic formula. You're envisioning letting u equal the cosine of theta, and in that case, for the quadratic formula, a is 6, b is 4, c is -3. If you substitute into the quadratic formula and simplify, that's one of the roots. Here's the other root. U is equal to the cosine. The angle that has a cosine, it's that value. Well, the cosine of some number is never going to be this. So we can reject this as a possibility and say the inverse cosine of this value should give us our maximum area. So there's the answer right there. We could apply the first derivative test to show that that generates a maximum. You could take the second derivative of this guy and show that substituting this critical number gives you a negative number, so concave downward, so maximum. There you go. Hope that helped. If you have any questions, post a comment.